Hello everyone, let's continue our learning from Kaggle. We have started into deep learning and we understood about a single neuron. Then we did a complete neural network and after that we have also learned how to apply any loss function and how to optimize any neural network using loss function and any optimizer. Right? All these things we have done as of now. And today our topic is overfitting and underfitting. As usual, we will first read out the tutorial, then we will do the exercise. Okay, let's read it line by line. Recall from the example in the previous lesson that Keras will keep a history that we saw some history function that is used to see that how a model is performing after every epoch, how the loss is getting reduced. You remember these things of the training and validation loss over the epochs. Exactly that it is training the model. In this lesson, we are going to learn how to interpret these learning curves. Okay, we saw the learning curves while plotting that the loss was getting reduced like that. So, we are going to interpret these things in this lesson and how we can use them to guide model development. In particular, we will examine at the learning curves for evidence of underfitting and overfitting and look at a couple of strategies for correcting it. Okay. Interpreting the learning curves. You might think about the information in the training data as two kinds, signal and noise. Signal means is that part that generalizes the part that can help our model make predictions for new data. That is the pattern, the hidden pattern. That is the signal. Like how our data is behaving with given conditions for the given features, right? And the noise is the true of the that is only true of the training data. The noise is all of the fluctuation that comes from the data in the real world. It's like that when you train a model, you can see that data follows a pattern, but with that, there must be some fluctuations, some random fluctuations that comes from the data in the real world. Okay, or all of the incidental, non-informative patterns that can't actually help the model make prediction, which actually deviate from the predictions. From the signal, we can predict what is the hidden pattern. So, what will be our future output? But noise exactly is the kind of randomness, but fluctuation that doesn't help you to make the prediction. But that is true, that is real. So, you always have to consider that also, right? The noise is the part that look useful but really is not. Now we train a model by choosing weights or parameters that we saw that whenever we are creating a model, we are using some weights W0, W1, W2. Those are the parameters we use to tune those W0, W1 and W2 so that the loss gets reduced. You remember these things? That minimize the loss on the training set exactly. You might know, however, that to accurately assess a model's performance, we need to evaluate it on a new set of data. That is the validation data. Okay, so you are keeping a different set of data. That is validation. That is not used for training. Okay, you have trained the model on training data part, but you are keeping a separate set of data like you used to keep for testing. Now you are keeping a separate set of data for validation data so that you can check how your model is performing. So you understand that your data set is divided into three parts now. Earlier it was training part, test part, but now we have created one more set of data which is the validation part. So training part, validation part, test part. All these data sets are different. That means a single data set is divided into three parts. Fine. Why validation is used? To see how the model is performing. Okay. Now, when we train a model, we have been plotting the loss on the training set epoch by epoch that we saw that after every epoch means what is epoch? You remember that when it goes through all the points of the data set, it is known as a epoch. Okay. Anyway, after every epoch, the loss will be reduced because we are tuning weights in that way so that the loss gets reduced and our model predicts better. Now, To this, we will add a plot on the validation data too. You have created a new data set for validation data. So you are similarly plotting on this validation data also. These are known as learning curves. Learning curves because after every epoch, it is learning something. It is reducing the loss. It is almost approaching the real output. Right? That's why these are known as learning curves. Now, to train deep learning models, we need to able to interpret them. Obviously, then only we will be able to improve our model. See, after every epoch, the loss in the training dataset is reducing this way. First, it will reduce in a speedily manner. After that, it will be kind of horizontal, right? But in case of validation, see what is happening. Loss is getting reduced, but after that, it is again getting increased. That means it is not performing right here because here the loss has reduced to the minimum, but after that loss is again increasing. Okay, so we have to make these things okay so that it gets reduced for training, it gets reduced for validation also. Okay, so the validation loss gives an estimate of the expected error on unseen data because this is unseen. Training data means the model has seen this data, and that's why the loss is getting improved, getting reduced. But this is not seen by the model. This is unseen. That's why after a certain time it is again getting increased. So we have to stop this one. Okay. Anyway, let's see. Now the training loss will go down either when the model learns signal or when it learns noise. Because in your data set, you have signal, you have noise. Signal means the true pattern, noise means the fluctuation. So here, as your model can see the data set, so it is learning the signal also, it is learning the noise also. But the validation loss will go down only when the model learns the signal. Learning the signal is the correct thing, so the validation is getting lost. Sorry, getting reduced. The loss is getting reduced. Okay, but when it learns noise, a gap is created in the curve. Here it is learning the noise, so there is a problem. The size of the gap tells you how much noise the model has learned. Okay. Right. So ideally we would create models that learn all of the signal and none of the noise. Ideally, but this is not problem. This is practically never happen. Instead, we make it trade because in your data set you must have signal, you must have noise. So you cannot do that you will learn the signal and you will never learn the noise. That will never happen. So what we you can do, you can find the balance, you can find the best of the two, you can do a trade. Now what we can do, we can get the model to learn more signal at the cost of learning more noise. So long as the trade is in our favor, the validation loss will continue to decrease. Okay, the trade is in your favor, so it will also decrease. The validation loss will continue to decrease, but after a certain point, the trade will go against you, so the cost exceeds the benefit and the validation loss begins to rise. Okay, now see here they have given two concepts, underfitting and overfitting. Overfitting means when your model is performing extremely well in the training dataset, but it is unable to perform in the test dataset. You understand the point. While training, it is doing extremely good. It is giving you a high accuracy. But when you are applying it on the training dataset, this performance is not satisfactory because it is overfitting. And why it happens? Like you think that you have memorized all the things, and in your class exam, all those questions have come which you have memorized. So you have performed extremely well. But what happened during board exam? The patterns are bit different. So what happened? You have not understood the concept. You have just memorized the thing. So you are unable to perform in the board exam. So you understand what happened. You have memorized the things because you have seen those questions. So what happens? See this data. The model has seen this data. So the model has memorized all the data. It has not understood the exact pattern. The exact pattern is the true curve, the dotted curve. See here. This is the exact pattern. This is how data is behaving. Okay. But what happened? The model has learned every point. So it has captured every noise, every signal, and it has overfitted the model. Okay. So this is a problem. You have to reduce this problem. How that we will learn later. And the next concept is underfitting. Underfitting means you are not studying at all. So you are neither performing good in the classroom exam nor in the board exams. Here also see this is the fitted curve, true curve, and this is the fitted curve. Just a simple curve, and both of them are like different from each other. Okay, this is the underfitting. The definition is that the model is neither performing well in training set nor in the testing data set. Okay, now let's read these things. This trade-off indicates that there can be two problems that occur when training a model. Okay, two kind of problem. Not enough signal or too much noise. That means you don't have enough signal or you have too much noise. In both scenario, you will face problem. Let's see how. Underfitting the training set is when the loss is not as low as it could be because the model has not learned enough signal. The problem is that the model has not learned at all. The model has not learned enough signal. It has not captured the value. So it is unable to perform. So the loss is not getting reduced. Fine. Next one is overfitting. Why overfitting? Because when the loss is not as low as it could be because the model learned too much noise. These are the some noise data points. See, these are just noise data points. So what happened? The model has learned the noise so much that here also the loss is not getting reduced. Okay. So there are two kind of problems. Not enough signal. If your model has not learned enough signal, you may go for underfitting. If your model has learned too much noise, it has learned everything, then also you are going for overfitting. And both of them are problems. We have to solve them. Okay. How to solve them? We have to balance. So the trick to training deep learning models is finding the best balance between the two. Okay, now let's read this. A model's capacity refers to the size and complexity of the patterns it is able to learn. For neural network, this will largely be determined by how many neurons it has and how they are connected together. Okay, so what happens if you use small number of neurons? That means you are studying for less hours. Like this way. This is not exactly related, but it will help you to understand. That's why I'm giving you the example. You are learning for less time. So what happens? You are not learning at all. So your problem is underfitting. Now the problem is second problem that you are studying for long hours and you are memorizing everything. Then you will fall for overfitting. Now read here. Model's capacity refers to size and complexity of the patterns it is able to learn. For neural network, this will largely be determined by how many neurons it has and how they are connected together. If it appears that your network is underfitting the data, you should try increasing its capacity. You can increase the capacity of a network either by making it wider or by making it deeper, adding more layers. Let me draw this for you. First, let's imagine that uh, you have a neural network, sorry, for two layers and you have two inputs. First input and second input. Okay, maybe this is x1, this is x2, and these are two neurons. And now there is output layer. So if I ask you how many layers do we have, how many dense layer do we have? One input layer and one hidden layer. And output. Output is not considered as a layer anyway. So two layers. Okay. Now suppose I want to wider. So I can increase the capacity of a network either by making it wider, that means adding more units to the existing layers. So this layer is already existing. What I am doing, I am adding the units. So I am adding 1, 2, 3, 4. Okay, and I am passing the inputs to them as well. Okay, you get my point. This is the way you are making the neural nets wider. Fine. Or making it deeper. How we can make deeper? By adding more layers. Like instead of having the output directly, what I am doing, I am creating more layers like this. And then I am keeping the output layer. Okay. So this way also you can join like this. You can join every node. So what is happening? Now you have more number of layers. This is also a dense layer and this is also a dense layer. Okay. So you can uh, increase the capacity of neural networks by adding more number of units or by adding more number of layers. So by making it wider or by making it deeper. Fine. Wider networks have an easier time learning more linear relationship while deeper networks prefer more non-linear ones, which is just better depends on the dataset. See, we did this before also. Keras library, sequential layers.dense. That is, you were creating a dense layer. 16, number of 16, sorry, um, number of units is 16, and the activation is ReLU function. For output, a dense layer and 1 unit. Because maybe you are doing a regression problem. Fine. Now you can make it wider. How to make it wider? By using existing layers. So, sorry, by using more units to the existing layers. So here you are increasing the unit. So you are making it 32 instead of 16, almost double. And sorry, double. And activation is ReLU. And the layer dot dense, this is for output. Okay. How can you make it deeper? By adding more hidden layers. Here first you have added 16 layers. Again you have added one more layer. First you have added 16 units to the layer. Again you have added one more layer of 16 units. Okay, so that's what I have explained you here. That's what they have done by coding. Here it is increasing the units. Here it is increasing the number of layers. Both of the way you can use for increasing the model's capacity. Now, which one you will use, that depends on the data set. Okay. For linear relationship, you may use the wider one, or for non-linear ones, then you may use that increasing the number of layers, making it more deeper. Okay. Now, next concept is early stopping. We mentioned that when a model is too eagerly learning a noise, the validation loss may start to increase during training. To prevent this, we can simply stop the training whenever it seems the validation loss is not decreasing anymore. Whenever you are training your model, you can see that it is getting reduced. But whenever you see that the validation is not getting reduced anymore, you can stop the training here, because you can also see that maybe in the training set it is performing well because it is able to see the data points, but here it is unable to see the data points. Your model cannot see these data sets, this data point. So what is happening? It is not performing well. The loss is not getting reduced. So though it may seem that it is performing well, but it is not actually performing well on the unseen data. So what we can do after we have reached the minima, after we had reached the minimum loss, minimum validation loss, we can stop training. Okay, so for that you have to see where it has stopped reducing the losses. There you will stop the training. Okay, so once we detect that the validation loss is starting to rise again, we can reset the weights back to where the minimum occurred. This ensures that the model won't continue to learn noise and overfit the data. Okay, here it is getting reduced. The loss is getting reduced because it is trying to memorize every point. So as it is learning each and every point in the data set, whether it is signal or it is noise, it doesn't matter. It is just a learning and the loss is getting reduced. It seems to be that our model is performing well. But the thing is that this is learning the noise, this is memorizing the things. And that's why on the unseen data, it is not performing well. Okay. Now, training with early stopping also means that we are in less danger of stopping the training too early because we are watching, then only we are stopping before the network has finished learning signal. So, besides preventing overfitting from training too long, early stopping can also prevent underfitting. Obviously, because you are not suddenly stopping here or here where model has not learned at all. So you are removing the underfitting problems also. You are removing the overfitting problem also. You are exactly catching the point. Okay. Now just set your training epochs to some large number and early stopping will take care of the rest. Very good. Now adding early stopping. How? Now we have learned what to do to stop the overfitting and to stop the underfitting. See here it is written as underfitting. If you stop here, it is underfitting. The model will be underfitted. If you stop here, the model will be overfitted. So you have to stop exactly here. But how? How to write the code? See for that you have to import early stopping. We include in Keras, we include early stopping in our training through a callback. A callback is just a function you want to run every so often when the network trains. These early stopping callbacks will run after every epoch. After every epoch, it will be called. Okay. Now, Keras has many predefined, but if you want, you can create your own. Here, see minimum delta, that is minimum amount of change to count as an improvement. They have set a point. Presence, after how many epochs uh, you will stop the training. And restore best words equals to true. Okay. Now these parameters say that if there has not been at least an improvement of 0.000 in the validation loss over previous 20 epochs, then stop the training and keep the best model you found. It means that if there is not 0.001 improvement, then you stop there. Don't train anymore. Okay, and now find where is the best fit model. What are those weights for that model was fitted best? Okay, it can sometimes be hard to tell if the validation loss is rising due to overfitting or just due to random batch variation. The parameter allows us to set some allowances around when to stop. As we will see in our example, we will pass the callback to the fit method along with the loss and optimizer. Okay, let's continue developing the model. We will increase the capacity of the network but also add an early fitting. Fine. Now let's increase the capacity of network. We will go for a fairly large network but rely on callback to hold the training once the validation loss shows sign of increasing. Okay. See here, early stopping equal to callbacks dot early stopping minimum delta, that is minimum amount of change that is considered as an improvement, and 20 epochs restore best words equal to true. Okay, now see here model is set. First, I have used 512 units, activation ReLU, input set, you know that number of features. Layer dot dense, the hidden layer dot dense, again hidden layer, and this is the output layer dot dense 1. Now you have used Adam optimizer and loss function MAE. It will calculate the loss. Okay. After defining the callback, add it as an argument in the fit. So we have to use model dot fit and extend y train. You have to pass the training data set, validation data now, x valid, y valid. I have told you that the data set is divided into three parts. That's what we are doing as of now. So now you have x valid, y valid also. Batch size you have provided and epochs means total number of your model will see the data points and here callbacks equal to early stopping. What we have defined here. Okay. Now, verbose equal to 0 means turn off the training log. History underscore df, where you have kept the history, that history, you are converting it into the data frame and now you are plotting that. So, you are plotting loss validation loss dot plot. Now see here, blue color is the loss and this one is the validation loss. Okay. And sure enough, Kira stopped the training well before the full 500 epochs. Okay. This is the maximum epoch. Uh, Before that, you have to stop it. Fine. Now predict your turn. Okay. Let's do the exercise. Okay, so what we have learned here? We have learned how to use the early stopping so that we can prevent overfitting and underfitting. Now, in this exercise, you will learn how to improve training outcomes by including an early stopping callback to prevent overfitting. Exactly when you are ready, run the next cell. We are ready, we have run. First, load the Spotify dataset. Your task will be to predict the popularity of a song based on various audio features like tempo, danceability, and mood. Import matplotlib plot.style.use for matplotlib set label size, title weight, title size. Learn tools.core, import binder, and all these things. Later on, we have imported pandas, standard scaling, one hot encoding, column transfer, spotify.csv, and then they have done some EDA part, see features, num features cat, then they have done the column transformation, group split. See here it has xtrain, x valid, y train, valid, and group split xy artist. Okay, now you have training data set, you have validation data set. Okay, fit transform for xtrain and for transform for and transform for x valid. Okay, and y train also you have, y valid also you do have. Okay, let's start with the simplest network. This model has low capacity because you are using small number of units. Now let me run this one. See, model equal to keras dot sequential layers dot dense one, only one layer. Model dot compile optimizer Adam, loss equal to MAE, and history equal to model dot fit. You send extend, y train, you send validation data, batch size, epochs, and verbose. Now you convert the history to a data frame, you plot it. Okay, now see what happens. Loss, validation loss. So minimum validation loss is 0.1951. It's not uncommon for the curves to follow a hockey stick pattern. This makes the final part of the training hard to see. So let's start at epoch 10 instead because you cannot see what is happening here. Okay, so we will start with epoch 10. Now let me run this. See what happens. Now you can visualize. This is the loss. This is the validation loss. Okay. Now evaluate the baseline. What do you think? This is underfitting or overfitting? Think. Okay. Before you see, you just pause it and think. This is the loss. This is the validation loss. Validation loss is lower than the loss. So it is overfitting or underfitting? Obviously it is underfitting. Okay. So let me run this. The gap between these curves is quite small. Validation loss never increases, so it's like underfitting. Once it starts increasing, then only we'll consider it overfitting, right now? Let's just see here. Here it is underfitting because it is not getting increased. When it will start increasing, then only we can see that this is overfitting. And why it is underfitting? Because we have not used any neurons, any units. So you have to add some units. Uh, add some capacity. So we will add three hidden layers. First 128 unit, then 64 and 1. Run the next cell to train the network and see the learning curves. Let me first run it. Compile optimizer Adam loss MAE model.fit extend y train validation data batch size given epochs given. You have converted it into data frame, you have plotted also. Okay, first check the history. See here loss 0.25, 0.24, 0.19 getting reduced. Validation lost 0.20, 0.19, 0.19 getting reduced. Very good. For how long? After that, see, after 0.2005, 0.2004, it has started increasing. 13, 13. Okay. So you can see that after this, training loss is getting reduced because it is memorizing the things, because it is overfitting the data, but validation loss is not decreasing anymore. Okay. So what is your evaluation of these curves? Underfitting or overfitting or just right? Now the validation loss begins to rise very early while the training loss continues to decrease. This indicates that the network has begun to overfit. At this point, we would need to try something to prevent it, either by reducing the number of units or through a method like early stopping. Okay. So where what we will do? We will use early stopping. So now this is your job. You have to write the early stopping function. Okay. So now define an early stopping callback. The wait epochs 5 patients for change in validation loss of at least 0.001 and keeps the weights with the best loss. Anyway, let's write this. Call to, we have to use the callbacks dot early stopping, and here write mean underscore delta equals to 0.001 comma, what are the other things? Patience. So patience equals to 5 epochs comma restore best weights. Let me copy this. Restore best weights equals to um, true. Okay, within 5 epochs. Okay, now let me run this. This is fine. You can see the solution from here also. Anyway, now run this cell to train the model and get the learning curves. Notice the callbacks argument in the model fit. 128 unit, second layer 64, activation ReLU, output 1, compile optimizer Adam, loss MAE, extend Y trend, validation, batch size, epochs. Now you are calling the early stopping which you have defined here. Okay, now you are plotting this also. See, it will go for 50 epochs, but within that you can see that after a certain time, what is happening? It has stopped. Epoch 12 out of 50, because here after this, it has stopped decreasing. Okay, it has not run for 50. Whenever it has found that the validation loss is not increasing, sorry, is not decreasing anymore, within this epochs, it has called the early stopping, and this one is executed. Okay, this is actually called after every epoch. So whenever it finds that the criteria is matching, it will stop and it will restore the best weights. That is the best model. Okay. Now was this an improvement compared to the training without early stopping? What do you think? The early stopping callback did stop the training once the network began overfitting. Moreover, by including restore best weights, we still get to keep the model where the validation loss was the lowest. Okay, so our job is to find where the validation loss is the minimum. This is this point we want to find. So that is done by the early stopping. It will check after every epoch, and whenever it can see that the validation is not decreasing anymore, it will stop the model and it will bring back those points where the validation loss was the lowest. Clear? I hope this is completely clear to you. And we have done it. If you like, you try experimenting with patients and mean delta. Okay. Just change the patients and change the minimum delta. Okay. And you can check out. Okay. I hope these things are clear to you and you have enjoyed the session. Let's meet in our next session. Till then, bye. Happy learning.